Hello everyone. Let's start today's lesson with something simple but powerful. Have you ever seen a playground seesaw, used a nutcracker, or even lifted something heavy with your arm? All of these are examples of levers at work. Levers are among the oldest machines used by humans. They make our tasks easier by either reducing the force we need to apply or by changing the direction of the force. The magic of levers lies in the relative positions of three things: the fulcrum, the load, and the effort. Depending on how these three are arranged, we get different kinds of levers. Today, we will explore the three kinds: Class 1, Class 2, and Class 3 levers. Before we look at the types, let's recall the principle behind levers. All levers work on the principle of moments. This principle says that when a lever is balanced, the clockwise moment equals the anticlockwise moment. In words, the equation is effort multiplied by effort arm equals load multiplied by load arm. Here, the effort arm is the perpendicular distance between the line of action of the effort and the fulcrum, while the load arm is the perpendicular distance between the line of action of the load and the fulcrum. This principle explains why changing the positions of fulcrum, effort, and load creates different lever classes. Let's start with Class 1 levers. In this type, the fulcrum lies between the load and the effort. Depending on whether the effort arm is longer or shorter than the load arm, this type of lever can either multiply force or multiply speed. Common examples include seesaws, scissors, pliers, and crowbars. For Class 1 levers, the formula for mechanical advantage is mechanical advantage equals effort arm divided by load arm. Similarly, velocity ratio is also velocity ratio equals effort arm divided by load arm. As you can see in the diagram of a seesaw, when the arms are equal, it balances easily. But when one arm is longer, it multiplies the effort or changes the motion speed. Next, we have Class 2 levers. In this case, the load lies between the fulcrum and the effort. This arrangement always gives a mechanical advantage greater than 1, meaning that the effort required is always less than the load. That is why these levers are called force multipliers. Examples include a wheelbarrow, a nutcracker, and a bottle opener. In each of these cases, the effort arm is always longer than the load arm, which ensures that the applied effort is multiplied. Now let's look at Class 3 levers. Here, the effort lies between the fulcrum and the load. In this type, the mechanical advantage is always less than 1. That means we need to apply a greater effort than the load. So why do we use them? Because these levers are speed gainers. They allow the load to move faster or cover a greater distance with a small movement of effort. Examples are the human forearm while lifting, a pair of tongs, or even a spade. As shown in the diagram of the human arm, the elbow acts as the fulcrum, the biceps provide the effort in the middle, and the hand lifts the load at the other end. Let us now solve a problem to make these ideas concrete. A wheelbarrow of length 1.2 meters has its fulcrum at one end. The load is placed 0.3 meters from the fulcrum and the effort is applied at the other end. If the applied effort is 200 newtons and the load is 600 newtons, calculate the mechanical advantage, velocity ratio, and efficiency. Step 1. Effort arm equals 1.2 minus 0.3, which is 0.9 meters. Load arm equals 0.3 meters. Step 2. Mechanical advantage equals load divided by effort. That is 600 divided by 200, which equals 3. Step 3. Velocity ratio equals effort arm divided by load arm. That is 0.9 divided by 0.3, which also equals 3. Step 4. Efficiency equals mechanical advantage divided by velocity ratio multiplied by 100%. that is 3 divided by 3 multiplied by 100%, which equals 100%. So in this case, the wheelbarrow behaves like an ideal machine. In practice, due to friction and other losses, the efficiency would be slightly less than 100%. Let's wrap up today's discussion with a recap. Levers are classified into 3 kinds based on the positions of fulcrum, load, and effort. Class 1 levers have the fulcrum in between, and they can multiply either force or speed. Class 2 levers have the load in between, and they are always force multipliers. Class 3 levers have the effort in between, and they are always speed gainers. The performance of a lever is measured using mechanical advantage and velocity ratio, both depending on the ratio of the effort arm to the load arm. From playground rides to construction tools, and even in our own muscles, levers are everywhere around us, quietly making our work simpler. I hope this session gave you a clear understanding of the different kinds of levers and their uses. See you in the next class with another exciting concept in physics.